Okay, today we are going to do some revision, okay, on some fundamental topics in mathematics which are very helpful for us to understand numerical optimization. So, okay, we will cover these three topics, okay, briefly, because I assume all this you have learned already. All the materials that we are going to cover today, you have learned them already much earlier, but just to revise, okay, before we dive into the more detail of the course. Okay, so the three topics include functions, metrics, and derivatives. Let's start with functions. So a function is something normally we write in this form. Okay, not exactly this one, but this form. Okay, we have a name of the function, we have some inputs, and then we have outputs. Okay, the outputs, how to define outputs, how we define the mapping of the function. What I mean here is a function is a mapping from this input, or which we call domain. Okay, from the input from the domain. Okay, and we map the elements in the domain, map the input, okay, to the output. Okay, the output is from the codomain. Okay, always from some domain to some codomain. The domain and codomain can be different. Okay, for example, mapping from integer to real numbers, mapping from real numbers to binary numbers. Okay, I mean binary 0 and 1 only. Okay, it's possible. Okay, so okay, yeah, one thing is, okay, the domain, okay, for function, all the elements in the domain, must be able to map to one element. Okay, each map to one element in the codomain. What I mean is, if I have another variable or another element here, 5, okay, and 5 is not able to map to anything here, then this is not a function. Okay, every element in the domain must be able to map to something in the codomain. Second, one element in the domain must be able to map to only one element in the codomain. I mean, if 1 map to 3, 1 cannot map to other element anymore. If you have 1 map to another element anymore, this is not a function. This is not a function. And the third one is, if you have more than one elements map to the same element, for example, both 4 and 5 map to 9, then this is allowed. This is allowed. Okay, but we cannot have multiple elements mapped to the one elements mapped to the multiple element in the codomain. Okay, some functions are so-called piecewise functions. Piecewise functions are the functions that behave differently in different spectrum of the input. For example, if you look at the graph here, okay, in this graph, some variables, okay, for example, those less than or equal to 1, okay, have different behavior, this curve, okay, and when they are greater than 1 but less than or equal to 2, it's always 3, right? And then when it's greater than 3, okay, you have different behavior. So this one is a graph, it's an example of piecewise function. We always write piecewise function in this form. Okay, for example, if we call the function f and the input is s, the fs is always, okay, the fs is a function that can be written in this form. I mean, when s is less than or equal to 1, this part, this one, okay, so this one here, okay, the function is s squared. When the function is between 1 and 2, okay, this part, okay, so it's always 3. And then when the function is something greater than 2, okay, fs is equal to s. So you see this one, this part, s. So this one map to here. Okay, so this is a piecewise function. Okay, some functions are multivariable function. Let's come back to here. You see, for this function, we have one variable only, x, right? What we know x, we know the output. We know x here, even though this is a piecewise function, we know x here, we know the output. It's either x squared, 3, or x itself. Okay, but some functions are so-called the multivariate function. Means this function, this kind of function, they have more than one variables. In this example, fxy, two variables here. Okay, both, we need to know both in order to compute the output of the function. We need to know both x and y. Otherwise, we do not know what's the output of the function, right? So this is so-called multivariate functions. Yeah, and some functions can be both multivariables and also piecewise. Okay, this is an example. Okay, in some cases, we want to group numbers into a rectangular array, okay, to process. In this case, we call this rectangular array a matrix. Okay, a matrix. So, for example, here we have a matrix. Okay, some cases. Okay, for example, when we have a photo, okay, we digitize it. Okay, we scan it or we take a photo on it. Okay, this photo, okay, digital photo, actually is a sequence, okay, of pixels. Okay, in rectangular form, right? And this rectangular form, these pixels in rectangular form, each one carries a value to indicate the number, okay, that represented by the color. So each color has a number, so we have a matrix here. This is a photo, is a matrix. So this rectangular array or this matrix always come with two numbers. One is the number of rows and one is the number of columns. Okay, so a matrix is always can be represented in form, okay, with number of rows and columns, n columns, m rows. So for each entry in the matrix, okay, we always, okay, if let's say we call this as A, the matrix A, all the entries in this matrix can be always written in this form, the Aij, okay, where A, okay, because of the this small letter of the capital A, and then Aij represents row I, column J. Okay, for example, 3 3, row 3, column 3, row 3, column 2, and so on. Okay, so we can do addition and subtraction on matrix, okay, as long as they have the same size. I mean, they have the same number of rows and same number of columns. So if these two are same, then you can perform addition and subtraction based on their position. What I mean is the first element, row 1, column 1, always add with the row 1, column 1 to get the result at the row 1, column 1. Row 2, column 1 to row 2, column 1 to get the row 2, column 1. Okay, scalar multiplication. Okay, there are two types of multiplications in matrix. One is a so-called scalar, the other one is a matrix multiplication. Okay, so for scalar multiplication, we multiply a matrix to a scalar, to a number, single number. So this one is very easy. We just bring in the number to multiply with all the elements in the matrix, okay, to get the result. For the second one, the matrix multiplication, okay, matrix multiplication, we always multiply two matrices with certain condition which fulfill. What's the condition? Okay, let's say we want to multiply two matrices A and B. We always have to check the dimension of the matrix. If the matrix A is m times n, m row, n columns, the matrix B must be a matrix with n row. The number of columns of the first matrix must always equal to the number of rows of the second matrix. Column of the first to the row of the second. Okay, and then the result of the multiplication is always a matrix with m row, the number of row of first matrix, b columns, the number of column of the second matrix. Okay, and then how to find the result of this matrix multiplication, or how to find the AB? This is what we do. For example, let's say at this position, row 1, column 1, okay, this is a matrix A, this is a matrix B. For row 1, column 1, you always find the row 1 in the first matrix. Column 1, you always find the column 1 in the second matrix. Okay, or for each of the element in this row 1 and the column 1, you multiply them and then sum together. Means this one multiply with this one multiply with this one, the result of the multiplication you sum together to get this one. Similarly, let's say for this one, you always find this is row 4, right? Row 4, and then column 2, column 2. So this one and this one multiply, this one and this one multiply, you get the result, you add, you sum up, you get this one. Square matrix, a matrix where the number of rows and the number of columns are always equal. Okay, we call them as a square matrix. For example, this is a 3 by 3 matrix. So since the number of rows is 3, column is 3 also, we call this as a square matrix. The elements in the what's the element in the matrix is not important. We always check the dimension only. Okay, and some special square matrix, we call them as a identity matrix. An identity matrix, okay, is a matrix, it's a square matrix. Okay, let's say this is 3 by 3 matrix, 3 rows, 3 columns. Okay, if the matrix has 1 over the diagonal, okay, all the value in the diagonals are always 1, and then others are all 0, we call this as a identity matrix with n equal to 3. That means we can write this as a I3. I for identity matrix. 3 because we have 3 rows or 3 columns here. So what's the big deal? Okay, identity matrix is a matrix such that if we have any matrix A times I, okay, is always equal to A itself. Okay, the diagonal matrix is a matrix where all the entries not at the diagonals are 0. For example, in this 3 by 3 matrix, okay, in the diagonal we have values not all 0, but all others are 0. This is a diagonal matrix. Okay, please take note, this one is not a diagonal matrix. Okay, why? Because we don't consider this diagonal. We always consider this one only. I mean, for the upper left to the lower right. Okay, this one is in the other way around. This is not diagonal matrix. Okay, but this one is also a diagonal matrix. Okay, even though we have more rows here, and this one is also a diagonal matrix, even though we have more columns here. Okay, a symmetric matrix. A symmetric matrix is always, okay, besides the elements in the diagonal, for all the other diagonals, okay, for all the for elements in all other positions, okay, Aij, for example, the element Aij, the value is always equal to the Aj. What I mean is, for example, this is A21, row 2, column 1. This is always equal to A12, both are 7. And then A31 is always equal to A13, and A32 is always equal to A23. Okay, so if all this fulfill, then this is a symmetric matrix. Okay, for some matrix, if, okay, the value of the lower triangle, I mean the value under the diagonal are all 0, we call this as upper triangular matrix. Okay, you see, in this example, you see this is diagonal. Okay, the diagonal and the value above the diagonal are some value which are not, at least not all 0, but the one under the diagonal are all 0. then this is so-called the upper triangular matrix. If, okay, something opposite, every elements, okay, above the diagonal are 0, then we call this a lower triangular matrix. Okay, transpose of a matrix. Transpose is a very simple operation. We just convert the number of row of an element to the number of column, and then the column to row. What I mean is, for example, if this is matrix A, okay, matrix A, the values in the first row is 1, 2, 3. Then, okay, you change the 1, 2, 3 to be the first column. Second row, 4, 5, 6. You change to the second column, 4, 5, 6. Third row become the third column. Okay, then this one is a transpose of the A. A transpose. We always write as capital T as subscript of the matrix to indicate this is a transpose. Some matrix we call them as a column matrix or row vector or column vector. Okay, for column vector, we have only one. It's a matrix with one column only. And for row vector, this is a matrix with one row only. Okay. Okay. If S is a column vector, this one means that S is a element of real number with n columns. Okay, n columns means that we have a total of n row here. Okay, then this is a column vector, okay, with n elements. So if this is the case, okay, if we find the transpose of the vector x multiply with the x itself, we will get a real number. You can see if this is a vector, the x, okay, this is the x, okay, and then x multiply, okay, right here, okay, perform the matrix multiplication. Oh, here, okay, here, okay, we perform the matrix multiplication, okay, with the S transpose first. S transpose become the row vector, right? Row vector and the column vector. 1 times n dimension, I mean 1 times n dimension, n row, n columns, and then you have n columns. N rows. 1 column here. The result will be always a 1 times 1. 1 n 1. We get 1. 1 times 1. So we get a real number. Okay. If we do it the other way, the s, okay, multiple, okay, or n rows, and then the transpose of it is 1. Okay, you perform the multiplication, you see this is a n times 1, 1 times n, so the result will always become a n times n matrix. N row, n column. Okay, n row, n column. Okay, so here, even, okay, if we multiply the transpose of x to a vector A, okay, and then back to the x itself, we also get a real number only. Okay. Okay, all the square matrix has a special number which we call them determinant. Okay, there are many ways to find the determinants of matrix, but we are going to introduce a very simple one, simple but recursive methods. So for example, if A is a 2 by 2 matrix, okay, so the determinant of A, okay, or sometimes we write this in this form, the determinant of A can be computed with A times D minus, okay, minus the B times C. Okay, so this is a very simple way to find the result or the determinant of a 2 by 2 matrix. If this is a 3 by 3 matrix, if this is a 3 by 3 matrix, 1 minute here. Okay, let's say A is a 3 by 3 matrix. A, B, C, D, E, F, G, H, I. Okay, the determinant of this matrix can be computed as follow. First, okay, let's say we start with the first number here. Okay, A multiply with the, okay, this is row 1 column 1, right? So this is the part that we don't involve the A at all. So A multiply with the determinant of this submatrix, EI minus FH. Okay, so A with this one, and then B, the second number is B. Okay, B, okay, this is the thing that involving B, right? So ignore this, all this, we have DI, okay, minus FG. Okay, and then the third one is, or the third or the last one is the C. So C, okay, C, we have C multiplied with the DH minus EG. Okay, so we have 3 groups number here. First, okay, first positive, second negative, third positive, and so on. Okay, but we have only 3 here, so stop here. Then this is the determinant of the A. So this is how we compute the determinant for 3 by 3 matrix. Yeah, it's a bit lengthy, but it's very simple. Just repeat. Okay, for 4 by 4 matrix, okay, or even higher, you repeat the computations, okay, as follow. Okay, the first number multiply with the determinant of this submatrix 3 by 3, then you have to jump to here to do the calculation and so on. Okay, so this is the way, okay, of finding the determinant of matrix. But of course you have to learn this. But in fact today we have many tools, include writing program, okay, using programming languages, or you can use a calculator, scientific calculator, to find the determinant of matrix. Okay, of course in the exam or in a test you can use a calculator, or okay, yeah, you can use a calculator. Inverse of a matrix. Okay, some square matrix, okay, has an inverse. Okay, I should repeat here. Only square matrix you can find an inverse, but not all square matrix has an inverse. Okay, so that means if you can find an inverse, that means this is definitely a square matrix. Okay, if A and B, 2 matrices, you find the matrix multiplication, and you find that AB is equal to BA and is equal to the identity matrix. That means if this is true, that means A, okay, is the inverse of B, or you can say B is the inverse of A. Same. Okay, so the inverse, okay, one rule here, inverse of an inverse is the A itself. Okay, and another thing is, if A and B are 2 different matrices, A and B here are 2 different matrices. Okay, maybe I don't want to confuse you, I use the other symbol. M is a matrix, N is the other matrix. You find the product of M and the inverse is always equal to N inverse product with the M inverse. Okay. Okay. One thing is, if the determinant of a matrix is 0, Okay, for all these square matrix, you can find determinant, right? Okay, if the determinant is 0, that means the matrix has no inverse. As I mentioned just now, not all square matrix has an inverse. Why? When the determinant of that square matrix is 0, that means that square matrix has no inverse. Okay, a matrix with no inverse, we call them as a singular matrix. If they have inverse, we call them as a non-singular matrix. How to find inverse? Very simple. From the definition here, you can find if A and A inverse equal to identity matrix, then using this one, okay, I think you should be able to find out a way to find the inverse of A. Okay, the next concept is a positive definite matrix. Okay, let's say we have a matrix A, a square matrix, dimension n times n, square matrix, and we also have a vector x with a dimension n as well. Okay, so remember just now we have mentioned that we have a transpose of a vector. We have transpose of a vector product with a vector if their dimension allowed. Okay, and then we product with the vector itself again. This one will always produce a real number. Okay, not a vector, not a matrix, but just a real number, scalar. Okay, so if no matter what x we use, okay, no matter what x we use here, okay, this matrix always produce a real number which is greater than 0. We call this matrix as positive definite matrix. Means we can change the x. Okay, we can use whatever x we want. Okay, but as long as it always produces a value, a scalar greater than 0, we call this as a positive definite matrix. If the value produced is sometimes is 0, it can be 0 or something greater than 0, greater or equal to 0, we call this as a positive semi-definite. Semi-definite can be 0. Definite, no 0. All positive result. Okay, all positive values, I mean. Okay, so the concept of positive definite matrix, okay, applies to both symmetric and non-symmetric matrix. Repeat, the positive definite matrix, okay, this concept applies to symmetric and non-symmetric matrix. Okay, but in this course we are only interested in the symmetric only, so we will focus our discussion on symmetric only for the positive definite matrix. So for the symmetric matrix, with dimension n times n, how we know whether this matrix is positive definite or not? Are we going to try all the possible x? Okay, no way, right? We can't finish because there are unlimited versions of the x, right? So we have 3 ways, okay, to determine a matrix is positive definite or not, if the matrix is a single symmetric one. First, we find the eigenvalues of the matrix. If all the eigenvalues are positive, then this is a positive definite matrix. Very simple. Just find the eigenvalues. Check whether they are all positive or not. Second, for all the value m, okay, in the matrix, you find the determinant of this submatrix, and if they are all positive, then this is a positive definite as well. What I mean is, okay, maybe I explain a bit. If this is a matrix, a square matrix, right? Okay, let's say okay, I use the example of 4x4. A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P. Okay, 4x4 matrix. Okay, for this matrix, what you need to do is you check. Okay, 1 minute. Okay, this color. is this first, is this a positive number? Yes, okay. Then the second step, you check if this one, okay, if this one is a matrix, is the determinant of this matrix, the purple one, if the determinant of this matrix is positive, if yes, then the third one is this matrix. Okay, we start from the this corner. We expand. Okay, is this square matrix the determinant of this square matrix? Okay, the 3 by 3 one has a positive determinant. If yes, and then lastly we find is this matrix, the whole matrix, okay, itself, the determinant is a positive. If yes, then if it is yes for all the four, then this is a positive definite matrix. Okay, this is the second way. And the third one, okay, we can write the matrix A as a product of two matrix. Sorry, one matrix actually. One matrix. The transpose of the matrix and the matrix itself. If you can write in this form, the matrix A can be written in this form, then the A is a positive definite matrix. Okay, but we won't go to this one, okay, because this one is a bit complicated. We will focus on these two. Okay, let's give you an example. Okay, for example, this is a matrix A. Okay, this is matrix A. So to determine whether the matrix A is a positive definite or not, first we find the eigenvalue of A. Okay, you find the eigenvalue of A, you find this is the 3 value, 1, 2, 3. Okay, this matrix has 3 eigenvalue. Okay, all the 3 eigenvalues are positive, right? So this is positive definite. The second way is, okay, we find, as I mentioned just now, we start from this corner, 7. Determinant of 7, of course, is 7 itself. Okay, greater than 0. Fine. Second, okay, we expand the triangle to this one. We find the determinant of this one, 7, 4, negative 4, negative 4, 5. So you see this one, the determinant is 19. Good, positive. Third, we expand the square to the whole matrix. We find the determinant of the whole matrix. You find that this is equal to 109, positive as well. So since all the 3 are positive, then this is positive definite. Okay, eigenvector and eigenvalue. Okay, let's say we have a vector. We call this vector as x. Okay, we can multiply the vector x with the scalar. Let's say we multiply with a scalar a. So after we multiply with a scalar a, we may get a vector which is maybe shorter or maybe longer, okay, or maybe at the same size. Okay, it can be different magnitude or same magnitude. If same magnitude means that the a is 1, right? So this is if we multiply the vector with a scalar. Okay, but we also can multiply the vector with a matrix. Let's say we multiply the vector with the matrix A, AS. Okay, if we multiply the vector with the AS, okay, most probably the vector, okay, will change to the other direction. Maybe this one, maybe this one, maybe this one, or this one. Okay, okay, this is quite likely. Okay, but for some matrix, okay, for some matrix and vector, after you multiply the matrix to the vector, you get back the vector, okay, with a different magnitude or even same magnitude only. Okay, so it's just like the method, the vector multiply with the scalar only. Okay, if this is the case, the lambda here, this scalar, we call this as the eigenvalue of this matrix, and the x here, this vector, we call this vector as the eigenvector of this matrix A. Okay, of course, A, when you say A here, A is it's always it's a square matrix. Okay, it's a square matrix, and of course the vector, the eigenvector here is a non-zero vector. Okay, S should be non-zero, because when it is zero, means everything is zero, means it is not something very significant, right? So S must be a non-zero vector. So okay, let's start from here. Okay, so you see just now we say AS. Okay, A multiplied with the S is equal to the lambda S, right? The scalar multiplied with the vector is equal to matrix multiplied with the vector. Okay, this one we can rewrite as this. Okay, because when you, okay, this is equivalent to a vector, okay, which is a identity matrix multiplied with the lambda, means all the vector. Okay, let's say this is a 3 by 3 matrix. Okay, that we have lambda, lambda, lambda here. Okay, so if we get, means the same thing. Okay, they are the same. Okay, so if this is the same, then we can move a bit. Correct now. Okay, and then we factorize this one, A minus lambda I S equal to 0. Okay, now we know that S is a non-zero matrix. Where is it? Okay, sorry, S is a non-zero vector. The eigenvector is a non-zero one. Because if it's 0, means everything is, okay, it will be 0 here and here as well. Means it's not significant. It's not something really meaningful, right? So this is equal to 0. Means what? Okay, means we need to find out what is it here. Okay, here you see there are two possibilities for this one, the one in the bracket, this whole thing. Okay, it can be singular or non-singular, right? Okay, non-singular means that the determinant is not 0. Singular means the determinant is 0, right? Okay, you see, if, okay, let me write this. If we multiply the whole thing with the inverse of this matrix, this one. Okay, if I'm up, sorry. Okay. Okay, you see this one, the whole thing here, this one, I multiply the inverse of this one is equal to, of course, is equal to this one, right? A minus lambda I inverse 0. Okay, you see from here, where is it? 1 minute, my mouse. Okay, you see this one. Let me find. Okay, this one, this whole thing. This is something inverse multiply this with this something. This one should be equal to I, right? Okay, identity matrix. Okay, inverse multiply with the matrix itself, you get in. Okay, IS is equal to, this one is 0. I is identity matrix, which is not 0. Okay, but S, after you multiply with the S, you get 0. Because this one multiply with this one, sure is 0, right? This one means what? This one means the S is 0. Okay, then we go back to here. S should be something not 0. So that means if this is true, that means this one, this one should not happen. This one should not happen as well, which means that this A lambda, A minus lambda I should be a matrix which is not invertible. Because if it is invertible, if it is invertible means you can write this. Means that you'll find S is 0. But since S is not 0, means that A minus lambda I, this matrix, is not invertible, or the determinant of A minus lambda I is equal to 0, not invertible. So if this is not invertible, okay, that means this one, okay, we call this as a characteristic equation. Okay, the characteristic equation with this one we can find. Okay, if we know A, means we can find the lambda. We can find the eigenvalue, and if we know the eigenvalue, we can find the eigenvector x. Okay, how to do it? Let's say A minus lambda I equal to okay. So what we need to do here is we substitute everything we know into the matrix A. Okay, and then we minus lambda I, means, okay, if let's say this is A is equal to A, B, C, D, E, F, G, H, I. Okay, means here we have the B, C remains, D, F remains, G, H remains, but those in the diagonal you minus with lambda I. I is all 1, right? Lambda I means all lambda. So A minus lambda, E minus lambda, and then I minus lambda. Okay, this one, the determinant of this one, okay, is equal to 0. Then if this is true, means if we can do this, solve this, means that we can find the lambda. Okay, if we first solve this, we can find the lambda, the eigenvalue, and then we can find the eigenvector. Okay, maybe we let's look at this example. Okay, okay, maybe I 2, 3, 3, negative 6. A equal to 2, 3, 3, negative 6. Right? What I mentioned just now is a determinant of A minus lambda I is equal to 0. Okay, here you look at here, this one means that, okay, determinant of A, 2, 3, 3, negative 6 minus lambda I. Lambda I is 1, 1. Okay, is equal to 0. So this one means what? Determinant of 2 minus, okay, make it short, make it easier. So this is just lambda, you multiply in lambda in, you get this one, right? So you have determinant of 2 minus lambda. Okay, 3 minus 0, 3, 3 minus 0, 3, negative 6 minus lambda, negative 6 minus lambda is 0. So we know this one, to find the determinant of this one, okay, 2 by 2 matrix is easy. So just 2 minus lambda, negative 6 minus lambda, minus 9 equal to 0. You solve this, you get, okay, you get lambda equal to 3 and negative 7. Okay, this is a equation. Okay, and then you find this negative 3 and negative 7. So the 3 and negative 7 are the eigenvalue of the matrix A. Okay, with the eigenvalue, okay, we can put back to the A, okay, to find the value of x. So you see here, this is again this is a characteristic function equation of the one. So you see this is A minus lambda, okay, this one, and the x is given here as a 2 by 2 matrix, 2 by 1 matrix or vector, column vector, okay. And then you see we do the matrix multiplication, okay, 2 by 2, 2 by 1, you get a 2 by, okay, you get 2 by 2 and 2 by 1, you get 2 by 1 matrix, okay, or vector. So because the lambda, okay, we have two value of lambda here, where is it? Okay, we have two lambda here, 3 and -7. Let's start with 3 first. Okay, let's start with 3 first. When lambda is 3, you put in a 3 here, okay, you get this one. Okay, 2 minus 3, -1, -6 minus 3, -9. Okay, you do the matrix multiplication, you get this one. What it means is you get negative x1 plus 3x2 and 3x1 minus 9x2. Okay, you do the matrix multiplication, you get this one equal to 0. Equal to 0 means that both are 0. So this one, the first is 0, the second is also 0. So if you get these two, actually this is a system of linear equation, right? So you can find what's x1 and x2, but actually you cannot solve. You find that you cannot solve. They are similar, but you can simplify it to x1 is equal to 3x2. Okay, you can find that this two means that simply means that x1 equal to 3x2. So that means any value of x1 and x2 fulfill this can be the eigenvector. Okay, if I choose x2 as 1, so we have 3x2 here, then x1 is equal to 3. So that means you can choose 3, 1. 3 for s1, 1 for s2, okay, to be the corresponding eigenvector for lambda equal to 3. Okay, you can change the lambda from 3 to 7, -7. -7, okay, you change the lambda to -7. Lambda to -7, okay, and you solve it, you can find, okay, the other eigenvector is 1, 3. For lambda 3, eigenvector 3, 1. For lambda -7, eigenvector 1, 3. Okay, so this is how to find the eigenvector and eigenvalue. Okay, some information here. The determinant of a matrix is a multiple of its eigenvalue. If you know all the determinants, okay, you can find. Sorry, if you know all the eigenvalues, you can find the determinant easily by multiplying them together. For example, here you find this one. The eigenvectors are 3 and -7, right? So the determinant of A should be equal to -21. Multiply them. Okay. If a matrix has eigenvalue 0, it is a singular matrix. This is very easy to understand. Okay, if there's a eigenvalue 0, that means the determinant, because the determinant is a multiply of the eigenvalues, right? So determinant is equal to 0 as well. So the determinant is 0 means that this is a singular matrix. Eigenvalues of symmetric matrix are all real numbers. Okay, if you have a symmetric matrix, then all the eigenvalues are real. Okay, if you have non-symmetric matrix, maybe some of the eigenvalue are imaginary value. Okay, if the matrix is a positive definite, okay, for positive definite matrix, all the eigenvalue are positive real numbers. Okay, derivatives. Okay, we move to a new topic. Let's say 5 is a real valued function of a real variable. That means, okay, phi is a function that map from real variable to some real value. Okay, both are real numbers. Okay, so if this is the case, we can find the first derivative of 5, okay, which is written as commonly written as d5. Let's say the variable in the 5 is s. 5, okay, let's say 5 is a function of s. Then we can write d5 ds. Okay, the d5 ds can be written as the 5. Okay, the s here, the variable s, okay, minus a small value epsilon, okay, minus the 5 epsilon. Okay, this one is the 5s. Okay, this one is the function 5 with which take the s as a input. This one is a function that s minus the epsilon as input, small difference, okay, and then divide by the epsilon with the condition that the epsilon is small. Okay, epsilon is small. So this will find us the derivative of the function 5. Okay, so it's common to write the derivative of function 5 as follow, or in some books you'll find they write this one. Okay, or in some books they write this with 1 dot. Okay, so this is the first derivative. For the second derivatives, okay, we do actually it's just follow what we have here. We do it another times. Okay, we do it another times. Then we find the second derivatives of 5. Okay, which stands follow, or in some books they write this one 2 prime, and then or some books they write 2 dots on the top. Okay, these are the second derivatives. I think you have learned the derivatives in the calculus. Okay, calculus courses. So these are some basic properties of derivatives. Okay, okay, these are those you have to remember: product rule, quotient rule, power rule, chain rule. Okay, power rule is something very simple. Okay, chain rule. Okay, product rule and quotient rules is something that you should remember. Okay, so and also these are some common derivatives for some special functions. For example, sine, cos, tangent, and so on. Okay, so these are derivatives for some common functions. Okay, for a function, for function, yeah, f. Okay, in some function we say some functions are multivariable functions, right? Just now we said it can be s, maybe y, or even more we have z. Okay, the function f of z is a function that involve all the 3 variables. Okay, and maybe some other constants. Okay, but at least 3 variables. Okay, we call this as a multivariable function. But more commonly, instead of writing s, y, z, we will group the s, y, z together to become one vector. Okay, or I say this. Okay, s. This s is different from this s. Okay, the s vector s it's a group of all the variables s, y, z here to be a vector. Okay, so we can write this as all the variables as one variable only, but this one variable is a vector. Okay, or this vector, instead of writing it as s, y, z, is easier to manage if we write the s. Okay, this s as, instead of calling them as s1, s, y, z, you call them as s1, s2, s3. Okay, which is easier to manage. Okay, so a function f, which is a multivariable function. In this case, this is this f. Okay, this f is a function from R3. Okay, because 3 variables s, y, z, or s1, s2, s3 to a single real number. Okay, R. Um, so for the case of vector, the x is a vector, or you still can still want to say this is a multivariate function, you can. Okay, for the case where the function has vector as input, the gradient, okay, the gradient or the derivatives of this function is given as follow. Okay, what I mean is if x is a three variable function, x1, x2, x3, okay, and we have f x, this x, the derivatives, okay, or yeah, one thing is we also can write it as this one, okay, nabla, this is a symbol nabla, not delta, okay, delta is this one. Some people call this as delta. No, delta is this one. The inverted one is nabla. Nabla f, okay, means the gradient of f, gradient of this function, fx, okay, is given by, since we have three variables, x1, x2, x3, okay, this gradient is a vector as well. So this vector is what? This vector is the first element is the df, okay, derive the function, okay, over x1. The second derive the function over x2, and then the third one is a df dx3. Okay, so this is the gradient of the function. Don't worry, later I will show you some example. Okay, this is a gradient, and the other one, which we call it as a Hessian. Okay, the Hessian is the gradient of the gradient. You can call this as a gradient of a gradient. Okay, which we call it as Hessian. Okay, let's start. Maybe continue from here. Okay, let me copy with it. Okay, this is the gradient of the function, and the Hessian of the function. The Hessian of the function, this is gradient. Hessian is the second derivatives, or you want to write it as a okay, also can, but this is not common. More commonly we write this one. Okay, we write this one. This is common. This is a common way of writing it. Just erase it. Okay, so this one is the derivative for this one. So this is a vector. How to derive it? So to derive this one, okay, 3 by 1 vector, after derive it, we will have a 3 by 3. 3 by 1 to become 3 by 3 vector. I just draw the boxes, okay, which is not supposed to show in the actual, okay, case, but I just draw it for you to see easier. So this one is df, okay, sorry, dx1 square, not square actually, second time. Okay, the first element is to be derived the same function with s1 2 times. Okay, and then this one is we derive the function first with the s1, and then the second times we derive with respect to s2, and then this one of course is d2f ds1, and then the second time we derive it over s3. Okay, so for the second row, same, derive of f over S2 first, and then followed by S1. D2F 2 times, both are respect to S2. D2F, the S2 first. Oh, this one I forward. Okay. The S2 first, followed by the S3. Okay, and so on. Missing D here. Okay. So this is a Hessian. Okay, but please take note. Please take note. This one. Okay. Wait. This one. Okay, and this one. Okay, which look different in the sequence. S1 followed by S2, S2 followed by S1. Actually, they mean the same thing. These two, okay, S1, S3, and S3, S1, actually same. And next one, S2, S3, and S3, S2, same as well. That means the Hessian, okay, the Hessian should be a symmetric matrix. They are always symmetric. Okay, so we are going to use Hessian a lot in our course. Okay, we are going to use Hessian a lot in the course, but luckily, all the Hessian we found, because of this symmetric, okay, they are always a symmetric matrix, and they have always possible to find whether they are positive dependence or not easily. Okay, so okay, just now what I show here is a example of 3 by 3 matrix. Okay, if it's a matrix with higher dimension, okay, this is the one. Okay, this is the one. If we have a higher dimension one, okay, some concepts or terminology here. Okay, for function f, okay, if we say f is differentiable on the domain D, that means for domain S, okay, for some value, let's say a to b, okay, from a to b, okay, you always can find this domain, okay, this domain, and when in this domain you can derive the function, okay, that means the gradient, okay, is exists for all the s in this domain, okay, that means this is differentiable in this domain. Okay, when we say the function is twice differentiable, okay, twice differentiable on this domain, that means we can find the gradient, the Hessian, okay, for all the value in D, okay, in this range, okay. And when we say this is continuously differentiable, that means the result of the differentiate one is the continuous function. Or when we say this is twice continuous differentiable, then that means it's a continuous function, okay, for this one. When this is true, okay, when this is true, that means the Hessian is a symmetric matrix. Okay, okay, let's look at this example. Okay, okay, let's look at this example. Okay, maybe I think I copy with okay, I just copy. So this is a function with two variables, okay, x, y. So to find the gradient, okay, to find the gradient of this function, okay, the gradient of this function with two variables, this is a vector, okay, a vector, a two-row vector. Okay, the first row, okay, is the one that we derive over x. Second row is the one we derive over y. So let's derive over x first. So this one you derive over x, you see x cubed become x squared. Okay, and then 3 you get 12. 3 times 4, right? 12 x squared, y squared remains, minus you derive signs, you get cos x. Okay, then the second is you derive over y. So y 2, 4 you have 8 x cubed y power 1, or just y, minus sin x. But sin x you derive sin x over y, you get 0. That's all. So this is the gradient of the f. How about Hessian? The Hessian of the f, okay, this is a 2 by 1, then you have the 2 by 2 Hessian. Okay, so firstly you derive this one, the one after you derive with respect to s, then you derive again over s. So derive over s, you have 2, 14, and 12, 24. Okay, 24, s squared become s, y still y cubed, y squared, minus, you derive the cos s, you get plus sin s. Okay, negative cos s become plus sin s. Okay, this is derived over the s, you derive over y to get this one. You derive over y, s squared become s, y squared become y, and then you have 24 here. 24 x squared y, okay, you derive over y minus cos s, you get 0, because this variable x, not y. Okay, you get 0. Okay, then this one you derive over y just now. Now you derive over s. Okay, you derive over s, you have 8 and 3, you get 24. X cubed become x squared. Y still y. Okay, and then this is derived over x1, x, and then now the last entry is you derive over y. You derive over y, you have 8x cubed only. So this is the result you find for the Hessian. Okay, please take note, this one you see as I mentioned just now, this one and this one same, right? Symmetric matrix. Okay, exercises. Okay, we have a few exercises here, a few questions, 6 questions here in total. Today I will just discuss, just give you a guide on how to solve this question. Okay, I won't go into very detail. Just a guide. You can try first. Okay, I advise you to try first. If you cannot, listen to this guide. Then only you just listen to this guide. After you listen to the guide, you try to solve it. Okay, on. If you still cannot, we can discuss it in the coming online session. Okay, so the first question is, let's say we have a vector 3, 5, v equal to 3, 5. Okay, so and given that fs is this one, find fv. That means we want to find f. We substitute s with v 3, 5, okay, into this s squared minus 2 modulus s. Just substitute the 3 and 5 to s, and then you get this is a vector with 2 rows, 1 column. Okay, just substitute s to here, so 3 to here, 5 to here, and then get this value and this value. Okay, question 2. If D is a 3 by 3 matrix, prove that D transpose is symmetric. Okay, this one, I've seen some students trying to do so. Okay, they just assume that 3 by 3 matrix is, let's say they try 1 2 3 4 5 6 7 8 9. Okay, and then they find the D transpose is what, 1 2 3 here, 4 5 4 5 6, and so on, and then find that okay, this is a result of something. Okay, they do a matrix multiplication and then find something. Okay, this is not a good answer. Okay, I wouldn't accept this as answer at all, because this is, you try to prove something. Okay, with a special example. When you prove it with some special example, doesn't mean that this is true for some other example, right? So we always don't prove something with example. We can only disprove something with example, but not proving something with example. So we have to do it in a more general way. Let's say you can just assume that this matrix is a matrix with variables A, B, C, D, E, F, G, H, I, and then okay, what is the transpose of the matrix? A, B, C, D, E, F, G, H, I. Okay, you find the matrix multiplication, the result of matrix multiplication, you get a matrix, and then you find, okay, if this is a matrix, okay, this one and this one are similar. This one and this one are not zero. I mean not zero. I mean some value here. This X, this X also. If this is Y, this is Y also. If this is Z, this is Z also. Okay, you find this. What are the values here, here, and here? Not important. But as long as this is true, as long as you find this one, you have proof this is symmetric. Okay, and then the question 3, if M is a 3 by 3 matrix and determinant of M is equal to N, okay, find determinant of alpha M, where alpha is a real number. Okay, you see, what we have here is a matrix that we do not know, but we only know that it's a 3 by 3 matrix, and then we know the determinant is N. The determinant of the matrix is N. Okay, so how to find the determinant of alpha M? So you should not simply assume that. The determinant of alpha M is equal to the alpha multiplied with the determinant of M. If you assume that, this you get wrong. No. Okay, maybe what you should do is assume that, okay, M is you can do it the hard way. Okay, if you want, you can do it the hard way for you to see easily. Okay, M, let's say you assume that M is this one, this matrix. Let me copy. How to wait. Okay, let's say you assume that M is this. Okay, so if M is this, determinant of M is, we can see from the previous example, determinant of M is A multiplied with the determinants of this one, E I minus F H minus B something plus C something, right? This one you can write out, right? And then how about the alpha M? The alpha M is this. Alpha M is this, right? So determinant of alpha M, okay, is equal to alpha A, okay, alpha A here, multiplied with alpha E, alpha I, minus alpha F, alpha H, minus what? Minus alpha B, and so on. Okay, then plus alpha C, and so on. Okay, you write down all this, and then you can find out that you can factorize this one. Factorize this one in the form of equal to something, okay, multiply with the determinant of m. Okay, try to find what is this something. Okay, so this is the question 4, sorry, question 3. And for question 4, if V is a m element, okay, column vector, and A is a m times m matrix, is this one equal to this one? Explain your answer. Okay, this one actually is very straightforward. I think you should be able to see that this one and this one should be not equal. Not only not equal, but in fact, if you, okay, if you can find this, you cannot find this. This is not defined, okay, because of the dimension problem. If you can find this, you cannot find this, okay. But if you can find this, you cannot find this because of dimension. Depends on V is a vector, column, or the column vector or row vector. Okay, depends on the V is a column vector or row vector. Okay, either this or this is the one only can find. Okay, if the m, of course, if the m is greater than 1. Okay. Okay, question 5. Determine the range of value of B, okay, in the following matrix if it is a positive definite matrix. Okay, so if this is a positive definite matrix, that means first we know the 3 is greater than 0. Okay, the determinant of this part is greater than 0 as well. Okay, we can see easily because this one is a multiplier of this one is positive, multiplier of this one is negative, but this is 31 minus 4, which is greater than 0, right? Still positive. But what we want to focus more is this one, the whole matrix. The determinant of the whole matrix is greater than 0. That means you have to find the determinant of the matrix, this one, and then this value is something greater than 0. You can find the B. Okay, or the range of the B, not a specific value, but the range of the B. Okay. And for question 6, find the gradient and Hessian of the following function at 2, 1. Okay, we want to find the gradient and Hessian at 2, 1. Firstly, we have to find the gradient and Hessian of this function in general form first. Then only we substitute s as 2, y as 1. So how to do it? Ln 1 plus x plus 2y. Okay. Xy equal to ln 1 plus x plus 2y. Okay, this is the function. So we find the first derivative or the gradient of f. Okay, so ln, since this is ln, we have 1 over 1 over, okay, we derive over the x. Okay, x is here. Because this is ln, we have ln 1 plus x plus 2y. Okay. Sorry, I think ln, yeah. Okay, wait, should be this one. No ln anymore. Okay. Okay. So refer back to the. Wait, refer back to this one. Yeah, you see, when you derive the ln, okay, you get ln x become derive it, you get 1 over x, right? So ln this one, you derive it, you get 1 over 1 plus x plus 2y. This is derived over the x. Okay, then you derive over y, you get same thing, 1 over 1 plus x plus 2y. But because of chain rule, okay, you have to derive it for this one also. Because x is only 1x, you get x as 1 as well. But this one, when you derive over y is 2y. So you have to derive the 2y, you get 2, multiply with 2. So this is the result of the first derivative, or the gradient, or it's more common to write in this for this way. Okay, this is the gradient. And how about the Hessian? Okay, you derive this over s again. You derive it over s again. So you should get 1 over 1 plus s plus 2y. Okay, chain rule, you derive, you get square minus. Okay, because this is a right negative, the denominator. Okay, so this is a negative, negative, because this is equal to negative. This one, I mean, this one is equal to power negative 1. Okay, and then this one you should be able to get derive over 2y. Same thing. But because of chain rule, you derive this one again, 2, you get 2, this one can 2. Okay, this one you can compute, this one you derive over s, but in fact this one, since we know this one is a symmetric one, this one and this one should be equal. Okay, seems like I give all the answer already. So the last one, okay, please compute for yours, to find out the answer. Okay, so this one should be derived, this one, okay, on y, with respect to y, I mean.